Okay, so we're going to look at transforming trig functions and the reciprocals. So I guess we'll focus on starting with the first original trig functions. And we're just going to quickly talk about what each of these letters are in reference to. So this formula, this funny looking f, essentially stands for any function. And that these variables, or these parameters, will affect any function the exact same way. Our first one, a, do you know what it will do?
Vertical stretch or compression.
Yeah, so we'll call it vertical stretch or compression. And it also flips, okay, on what axis? Do you know?
Axis.
Yeah, flips, we'll call it on the x. So flips x. What about k?
Horizontal stretch or compression.
Yeah, horizontal stretch or compression.
And flips on the y-axis.
That's right. Flips on the y. Good. D?
Translation left or right.
Yeah, so I'm just going to use that arrow to represent that. And C therefore does?
Translation up and down.
Yeah, and essentially the idea is the values that are outside of the immediate x values will do anything on our y, and anything inside affects horizontally our function. Okay, so let's say we have our function, our sine wave here, our original sine wave. Okay, so we're quickly going to show our sine function here, which essentially has, no, not that incorrect. Our sine function here has this type of relationship, right? Okay, and it continues this pattern. And that would be essentially our f at x is equal to sine. Okay, and in this case, our a value would be 1. Our k value would be 1. Our d value, did I do that in green? I think I did. Would be 0. Minus 0, I guess, technically. And our c value would be 0. So depending on how we affect these, is going to change our sine function, right? So if I put in a value here or here, this one will move our function. So essentially what I have here. And I could show the whole function, but sometimes it's easier if I just cut it into a piece and show you when a horizontal shift moves it. Sometimes it's easier to see because this is a repeating pattern. And if we start doing things like this, it gets a little confusing on what's happening. Okay, so let's say we were to change this value. I decided to go f at x was equal to sine. And in this case, I'll do x plus 2. That's going to move our function in which direction? Do you know?
To the left.
Yeah, to the left. How many?
2 units?
Yeah, 2 units, which is a really hard amount to talk about here. Okay, so what we do instead is usually when we do these shifts, because we're in radians, we transform them into radians. Okay, so if I'm talking about maybe I was thinking of 2 squares here, and I wanted this to shift by 2 squares. How much is one of these squares? What does that represent?
Pi over 4.
Yeah, pi over 4. So what would 2 of them represent?
Pi over 2.
Yeah, excellent. So I want a shift of pi over 2, which is similar to a 90-degree shift. My whole function would move 90 degrees, or pi over 2, to the left. So this one moves over. This one moves over 2. Over 2. And over 2. I'll get rid of that other one in a sec. But this is our function. And this one goes over 2. Okay. So here's our function. It is essentially shifted to the left. Okay. Same idea, and we're going to get more complex. I just want to do one at a time to make sure we understand this. Say we had sine, and in this one we're just talking about x plus 3. And I'm actually going to change that to minus 3 because I don't have that kind of room where we are. Minus 3. What does that do to the function?
Shifts it 3 units down.
Yeah, exactly. So this one shifts down to negative 3. One shifts up to negative 2. Negative 3. This one goes to negative 4. And negative 3 again. So very similar to what we had before. From our one that was originally drawn in black, we've shifted down 3 units. So to the left 3 units. This one here, we went to the left, pi over 2. Okay? And our compressions and stretches. Let's say we have f at x is equal to, and we'll try to do 2 and 1 here. We'll say negative 2 sine x. what does negative 2 sine x do to this function?
It flips about the.
Yeah. So our zeros are all the exact same. The only difference are this positive 1 will go to negative 1, and this negative 1 will go to positive 1. So in other words, this relationship. And then what does the 2 do?
It vertically stretches it by 2.
Yeah, vertically stretches it by 2. So instead of going to negative 1, we go all the way to negative 2 and to positive 2 here. So we'll put these in red. Okay. So it goes down to negative 2, up to positive 2, and then back. So this relationship has flipped it and vertically stretched it. Excellent. And then finally, hopefully we can get this last one in here, f at x. Let's say it's the exact same idea, but in this one it becomes sine bracket negative 2 x. Okay. What is that going to do to our original one in black here?
Flip it about the y-axis.
Yeah. So instead of me I could technically kind of flip it. I'm going to flip it on the y-axis. So I'm going to move the entire thing over. So it's going to essentially make this type of relationship. Okay. So now we're on the left of it because we have lots of room there. What does the 2 do?
Horizontally compress this by a.
Yeah. So it's the opposite idea here. So if we horizontally compress it, what does that mean for each of these values? For instance, when I get up to here, what can I do? Because radians is actually an easy one to use it with. What can I do with the denominator of this fraction to get a better idea of where it originally reached? Do you know what we can do? For instance, this point of 1, where would it be in the x-axis now? Do you know?
At negative pi over 4.
Yeah, and essentially what it means is I take this 2 and I can just multiply it by the denominator, right? If I do that through all of them, it'll give me very different values. So we know it's going to flip over this way. It's also going to be compressed. So instead of being up here, it's actually moved over, right? So we've cut the value in half, and we're going to cut each of them in half. So what color did I do this? I did that one blue, so let's do it in blue. So we now start here at 0. And a half for here. To cut this in half, it's essentially 1 times 2, so it becomes 2. So it goes here. And another way you can think of this is 1, 2, 3, 4. As long as it's drawn properly, we just split 4 in half, and we come to the 2 value, right? So we're now back down to here. But just like we did here, we had 2, we cut in half, it's now at the 1. This one here is at 4, 5, 6. If we cut 6 in half, we'd be at the 3 value. So that would be 1, 2, 3. This new value, whatever was here, will be essentially here. Now I know I'm not showing the y's with it, but I'm showing a fast way to do the x's where we can just kind of cut everything in half. So we have our values. This one was cut into 3, and our 2 is at 4. So it has horizontally, that's a poor example, but horizontally compressed what we've done and flipped it on the y-axis. Does that make sense then?
Yeah.
Yeah? Okay, so since we understand that idea, let's get into this. So let's talk about sine. And, we've just done sine. So cos being a very similar function has roughly the same tendencies, right? Depending on what I do, if I want to shift it to the right, we would do cos and then bracket x. If we want to go to the right, plus pi, I have that option, here we go, pi over 6, and we have a movement to the left. Did I say left before or right?
Left.
I said left? Okay, good. We have a movement of pi over 6 to the left, right? That's that similar idea. Let's say we wanted to move it up 3. It'd be plus the value of 3, and the whole function has moved up 3 units from where it originally was. So those affect it the same way. Does that make sense? Okay. Now the one that's a little different is tangent, because tangent has asymptotes. Okay, so let's take a look. Let's see what happens when we do the same ideas. So we'll talk about a vertical stretch of tan. Let's say we want a vertical stretch of 2 tan x. 2 tangent x. Okay. This vertical stretch of every single one of the y values is now 2 points higher. And it'd be nice if I could show you a good one here. Well, I can't quite hit 1. this value here. This value to here at where it would be, actually this x value here is the best way to show it. It's at negative 1.36 at negative 7.22, so we'll try to jump down 1.36, or sorry, negative 7.22, right? This is about 2 times as large as where we were before. Okay, so it's pulled it, think of like an elastic, it's pulled it up by that value there. Okay, let's change this a little. Let's see our horizontal stretch of 2. Okay, it happens in this tan function to push everything to the right. Now it looks like it's a vertical stretch, but actually everything's been compressed in these values here. And if you also notice, it's occurring much more often. Okay, where in our original one, it's changed our asymptotes, and that's what's important for this. Our asymptotes have all changed. Okay, and let's take it away for a second. If we look, remember we had an asymptote at negative a half pi over 2 and positive pi over 2. Here, we're actually hitting 0 at those points. And our new asymptote is occurring twice as often. So instead of being at pi over 2, let's see if I can get it, it's technically at, I won't actually reach it, but it's getting closer and closer to pi over 4. Okay, just like we talked about with the sine, we can multiply the denominator by 2. It's occurring twice as often, our asymptote, okay? And therefore changing the way our tangent occurs. It looks like it's occurring much more often, okay? If we're going to shift it, plus, let's say pi over 2. It's a good value, sure. All that's happened is our horizontal asymptote has shifted to the left pi over 2. So before where it was, our original asymptote was pi over 2, it's now moved to the value of 0. You see our red one is the one we're referring to. It has an asymptote right there. So everything is shifted to the left. So when we're talking about tangent, essentially we're really focusing on the asymptotes and moving those asymptotes whenever we have a horizontal shift. And whenever we have a vertical shift, we're again applying it. Same idea. Let's go plus 3. This point here, all right, our inflection point is essentially 3 units higher. Okay, does that make sense? Okay, so since we've learned about that, that's going to give us actually a good leeway into cosecant, because cosecant also has asymptotes. Okay, so as we manipulate cosecant, if I go by 2, it kind of stretches it. Okay, and it stretches it to where originally sine 2 would occur. So see how sine 2 has been stretched? It's actually changed its low point to be at that exact same point. So our high point of sine is also our low point of cosecant. Okay. If we were to, same idea, a value of 2 here. This is occurring twice as often. Very similar to if we'd done this with sine. And sometimes it's best with the reciprocals to originally graph them and then from there get a good idea of our major points if we're going to sketch it. We still know that wherever the zeros are going to be our asymptotes. Excuse me. Thank you. Wherever the zeros are going to be our asymptotes, right? And it's occurring twice as often. So our asymptotes are occurring twice as often with cosecant. Our other values that are just going to move things left and right essentially do the exact same stuff as before. So let's say we go negative. I guess I have to do pi here. Negative pi over 2. Okay. And in this case, our negative pi over 2, let's change that. Has shifted all of our asymptotes the same way. Negative. What if I can just copy? Beautiful. All right. So sometimes, like we said before, it's easiest if we draw the original and then draw our reciprocal from there with our graphs, because they're all roughly relating the exact same way they originally did. So it can be hard if we don't have the original in to see what that relationship's going to be. And if we shift it up, it shifts up, right? So I'm just going to add a shift to this. Plus 2, exact same relationship as before, right? And that would be the same for cos and secant, Okay, but what about cotangent and tangent? Okay, cotangent and tangent. Let's see what happens here. If we do a value of 2, we know that it stretches it that way. For cotangent, it does the same way, just inverting, going the opposite. Okay, so as the same type of relationship, our asymptotes have not changed because this is a vertical translation, right? Just like if we're moving, or sorry, a vertical stretch. If we were to vertically move up 2 and vertically move up 2, same idea. Okay, technically our asymptotes have not changed here. And we'll go back to where tan was originally. Okay. Our asymptotes have not changed. For our green, we have an asymptote at pi over 2, pi over 2. And here our asymptotes just changed where the 0 are. All it's doing is shifting both units up. Now, where our difference is going to be is with our horizontal translations. Our horizontal translations, Control B, let's say minus. Okay. So if you notice here, it looks like it's in sync with the black, but technically that's not originally where our cotangent was. Our cotangent makes this relationship. So essentially it's moved those asymptotes to the right 90 degrees, or pi over 2 in this case. So the whole thing is moved. And these ones are harder to see because they don't visually relate the way sine and cosecant do and cos and secant do. Okay, so it's going to be a little harder, but again, the original tangent does give us a pretty good idea. And finally, for our times 2, our asymptotes are just occurring twice as often, right? So all roughly the same thing. We really got to focus on our asymptotes for tangent, cotangent, cosecant, and for secant.